So now we're going to look at something called the difference between statistical significance and practical significance. This is a really big issue in looking at any kind of statistical study, is to be able to distinguish between these two types of significance. We already know statistical significance means the observed results are unusual under the assumption the statement in the null hypothesis is true. That's what statistically significant means. You observe results that are unusual under the assumption the statement in the null is true. Practical significance, on the other hand, refers to the idea that while you have small differences between the statistic and the parameter stated in the null are statistically significant, so even though you have statistical significant results, the difference may not be large enough to cause concern or be considered important. So in other words, you obtain evidence that tells you the results are statistically significant, but the differences aren't enough to make you feel like it's really that big of a deal from a practical point of view. So let's look at an example of this, and then I'll elaborate a little bit on this. In 2003, the average age of a mother at the time of her first childbirth was 25.2 years of age. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 years of age, with a standard deviation of 4.8. Determine whether the mean age has increased using a 0.05 level of significance. So again, we're going to go through our tests, but this time I'm going to go kind of quick. First of all, the variable of interest is age of the mother. We're wondering whether the mean age of a mother today has increased relative to the mean age in 2003. The statement of no change, no effect, no difference is that the mean age today would be the same as it was in 2003. That would mean no difference. And that would suggest that the mean age is how much?
25.2.
Yeah, 25.2. We want to gather evidence to show that the mean age has increased. So we want to know if the mean age is bigger than 25.2. Step 2, we have a 0.05 level of significance. Step 3, I'll just verbalize the requirements. We have a random sample of 1,200 mothers. Our sample size is very large, and so that would suggest X bar is approximately normal because of the central limit theorem. And then there are I think there's something on the order of 3.8 to 4 million births annually in the US. So 1,200 is certainly less than 5% of the population size.
Satisfies that.
So that's good. And so now we can go ahead and use StatCrunch to estimate the p-value. So in StatCrunch, we select stat, t-stats, one sample. We have summarized data. The sample mean from the problem was 25.5 years of age. The sample standard deviation, 4.8. The sample size was 1,200 mothers. The mean stated in the null hypothesis is 25.2. And we had a greater than alternative. Click compute, and we're getting a p-value of 0.0153. The p-value is small, right? It's definitely less than the level of significance. And so we are going to reject the statement in the null hypothesis. Right, so p-value is less than level of significance, which was 0.05. Therefore, we reject the statement in the null hypothesis. And so there is sufficient evidence to suggest the mean age of a mother has increased since 2003. So it is a statistically significant result. However, ask yourself, is 0.3 years, and to give you a sense of this, 0.3 years is 3.6 months. Do you think a mother waiting 3.6 months before having their first childbirth is really that big of a deal? 3.6 months. I mean, that's, yeah, no, not at all. And so these results, while statistically significant, really have no practical significance, meaning it's not like you'd get on the news and say, wow, the age of mother has gone up almost 4 months. People would be like, who cares? Big
Right.
deal, right? And so there's really no practical significance in these results, even though they have statistical significance.
So would you consider like 4 years then, like practically significant then?
That's a great question. How do you judge practical significance? It's called effect size. Effect size is what professionals in the area of study deem to be practically significant results. In any kind of study, you really want to have access to an expert in the field in which you're studying to tell you what would be considered to be an effect size that you're looking for.
Okay.
Right? Now, in this example, I don't know who you'd go to, a sociologist, or I don't know who you would go to for that, or maybe it's up to you as the individual researcher. Well, I'd say an effect size of a year or maybe a year and a half is something that I'd consider to be practically significant. I don't know, right? That's not the job of the statistician in this. It's the job of the expert in the field.
But the statistician wants to find out from the expert what would be practically significant then.
That is correct.
Okay.
And the word for that is effect size.
Effect size. Okay.
Effect size. Not A, E. EFFECT. Effect size. And so you definitely want to have that in your mind. You know, the folks that are taking this intro class, obviously we're trying to give you the background of what it means to do statistical analysis. Odds are, you know, you're going to be either reading research articles, or maybe down the road when you get more in advanced areas of your discipline, field, you'll be involved in some sort of data collection studies. That's why we're teaching you these words, not because you're going to be doing it, but that you're going to be looking for that kind of thing. Somebody might come up to you and say, what effect size am I looking for? And you're going to say, oh, wow, I remember Sullivan telling me about that. But that's the idea there is that plays a big role. So that's number one. So that was a great question. Second thing, why were we able to reject the null hypothesis? Or why, in other words, why were these results statistically significant even though they had no practical significance? That came from the fact that our sample size is massive, 1,200. With a sample size of 1,200, your standard error for this particular problem, remember standard error is S over the square root of N. So our standard error is 4.8 over the square root of 1,200. So you can imagine a large sample size causes your standard error to shrink tremendously. This is giving us a standard error of about 0.14. So a sample statistic to be 2 standard errors away would only require 0.28 years. Right? 2 times the 0.14 would put you 2 standard errors away. So the larger the sample size is, the smaller your standard error is, and therefore the more likely you are to reject the statement in the null. Not because the statistic is really, really far away in absolute terms, in other words, in a decent effect size, but rather it's far away because you caused your standard error to be so small that you're inevitably going to end up rejecting the null. Think about it like this from a graphical point of view. Here's where I'm assuming the mean is 2 standard errors away. When you have a sample size of 1,200, 2 standard errors away is at 25.48. From a statistical point of view, 25.48 is far away from 25.2.
Right.
From a practical point of view, it's not.
It's very close.
Close. And so that gets to when another thing to look at when you're looking at studies is take into account the sample size. Studies with very, very, very large sample sizes will inevitably lead to statistical significance because your standard error becomes so small. Be hyper skeptical of studies that claim statistical significance when the sample size is massive, is the moral of the story. I mean, this to me is one of the bigger issues to learn out of this course.
Mm-hmm. Are you saying the statistical versus practical?
Yes.
Okay.
Yeah. You'll see it all the time. Another place I've seen it is in test prep studies where, I'm a test prep organization and I'm trying to improve your SAT or ACT score. And they'll say 10,000 students that took our exam scored significantly higher than the students that didn't.
Mm-hmm.
Right? And it's not because they really scored significantly higher from a practical point of view. It's just because they looked at 10,000 students and that caused the standard error to be teeny tiny. Right?
Wow.
I mean, would you want to go through a whole test prep if it caused your ACT score to go up 0.1? Right? But you could show that to be statistically significant with a large enough sample size.
Wow.
So that's where stats gets a bum rap, is people use it for evil instead of good. So it's important to be statistically literate for that reason.